Good morning, pre-calculus 30. Just before you begin watching the rest of this lesson, I would ask that you complete the Investigate Transforming an Exponential Function on page 346 to 347 of your text. Then answer the reflection and response questions that you have in your student book. I'll get you to pause the recording until you're ready to continue. Okay, let's move on with lesson 2. We're going to cover these reflect and respond questions, which should have been fairly familiar to you because we've already talked about movement within our basic graphs, and now we're just doing it with exponential graphs. So the first thing that we talked about is the roles of h and k in our functions of the form f of x, or some function equals some number times our base to the power of our horizontal stretch x minus h plus k. And you should have noticed that both h and k are your translations. H moves you left and right, whereas k moves up and down. You also should have noticed that a negative h value here will move you to the right, while a positive h value will move you to the left, just like we've seen in every other example this year. Now they ask us to look at A and B. So we're looking at A and B here. So A and B, we can see are multiplied, so those are our stretches. So A here is our vertical stretch. So you would take all of your y's multiplied by A. So A equals your vertical stretch. And B here is your horizontal stretch. Remember that with your A's and B's, for B, you are actually going to multiply your values by 1 over B, not simply B. Okay, so now we're going to look at our two basic functions here. So y is f of x equals negative outside the bracket 1/2 x, 1/2 to the power of x, considered an exponential function, but f of x equals bracket negative 1/2 to the power of x naught. So this is not an exponential function because your base is negative. This, however, is an exponential function with simply a reflection. Okay, so what we see here, this is simply a reflection. Whereas on this one, we see a negative base, which does not give us an exponential function. So for a note, you can go to page 348 in your text, and this gives you a visual of what each thing is going to do. Okay, let's talk about reflections and stretches when we are actually graphing. So transform the graph y equals 4 to the power of x to sketch the graph of y equals to the 4 to the power of negative 2 bracket x minus 5 plus 3. Describe the effects on domain and range, equation of the horizontal asymptote, x and y intercept. So you have a choice. You can either map or you can move each step. We're going to map it because I like to map, so we're just going to map. So our first graph is y equals 4 to the x. So that's the first thing we need. We need some points, x and y. So we're going to take x is negative 2. We're going to take x is negative 1, x is 0, x is 1, x is 2. Now when I plug those in, 4 to the power of negative 2 is going to be 1 over 16. 4 to the power of negative 1 is going to be 1/4. Anything to the power of 0 is 1. Anything to the power of 1 is itself. and 4 squared is going to be 16. So our next step in transforming this, we are going to take our do our stretches. Okay, so we have one stretch, it's right here, and that is actually within our function. So we need to multiply our x values because it's not out front, it's within our brackets. So we're going to take all of our x values and multiply them by negative 1/2. Okay, so when I take these x values and multiply them by negative 1/2, I'm going to get negative 2 times 1/2 times negative 1/2 gives me a positive 1, comma 1/16. Negative 1 times negative 1/2 gives me 1/2.
Miss Ukraine, could you
1 over
please
4.
call 117? Miss Ukraine, please call 117.
This will be 0 and 1. This will be 1/2 and 4, sorry, negative. And this will be negative 1 and 16. So now that we've dealt with our stretches, we can work with our translations. So our first translation, we are going to subtract 5 from our x's, and we're going to subtract 3 from our y's. So negative 5. I'm having a lot of trouble with this thing today. It's not making me too happy. So we're going to have negative 5 plus x and negative 3 plus y. So our new points that we're going to wind up at will be negative 4 and negative 47 over 16, which, let's do decimals because we don't know how to graph 47. Well, we do, but we don't want to. Oh my goodness. I'm going to flip on this thing. So I take, negative 5 plus x, negative 3 plus y. So then we have negative 4, comma, negative 2.9. Then we wind up with negative 4.5, comma, negative 2.75. Then we wind up with negative 5, comma, negative 2. Remembering that's positive 1, I just can't write very well on here. And then negative 5.5, 1, 6, negative 6, and 13. So this point can be graphed, this can be graphed. So we wind up getting a graph that looks similar to this. Okay, so when you plot your points, they'll look something like this. Okay. Also notice these are still going to approach an asymptote, and what I need to do is shift my asymptote according to my my y shift. My original asymptote was at y equals 0, so now it's going to shift down 3. 1, 2, 3. So my new asymptote is at y equals negative 3. So then I can draw my exponential function approaching y equals negative 3, but never actually reaching it. So there you go. Looks sort of okay. So just a note on that asymptote. Your asymptote is y equals negative 3 because it shifted down from y equals 0. Okay. Let's talk about our domain and range. Just going to erase this work in here. Okay. So for domain and range, how does this change this? Well, my domain is still, x can be all real numbers, so this is no change. My range is now y has to be greater than or equal to negative 3 instead of y has to be bigger than or equal to, sorry, bigger than 0. So this goes into your equation as well. Your horizontal asymptote is now at y equals negative 3. So this is 3 down from y equals 0. Your x and y intercepts, well, we actually have an x-intercept, you can see now. So we do have an x-intercept. You can calculate that by using an intersection. And our y-intercept has also changed. Our original y-intercept is always 0, 1, but we can see that it's actually shifted down. Okay? So if I wanted to find my x-intercept, I could actually find the intersection with y equals 0. And if I wanted to find the y-intercept, you simply have to enter, when you get to your graph, if you just press 0, it'll trace to where your x equals 0, so it'll give you this point. But since we're not too focused on that, I'm not going to go through it. Okay. So exponential growth and decay can be modeled using this formula. A, or the amount we want in the end, the future amount, equals our initial amount times our type of growth to the power of the elapsed time divided by the period for the growth to occur. Okay? So for example, if bacteria doubled in 4 hours, I would say that B is 2, P is 4. Okay, and then T is going to be in hours. So if our radioactive sample has a half-life of 8 years, my B would be 1/2, my P would be 8, and my T would be measured in years. If a population triples every 10 years, my B would be 3, my P would be 10, and my T would be in years. Now this makes writing those equations for your word problems a little bit easier. So let's try a word problem. The radioactive element, americium, is used in household smoke detectors. Americium-241 has a half-life of approximately 432 years. So that means after 432 years, half of your original will be present. The average smoke detector contains 200 micrograms of americium-241. What is the transformed exponential function that models the graph showing the radioactive decay of 200 micrograms of americium-241? Okay, so we have our basic formula, A equals A naught times B to the power of T over P. So my A is my future amount. That's what I want to model. So I'm going to say A, because that's what I want to model, equals A naught is our original amount. Originally we have 200 micrograms. In brackets, B is how it's behaving. So this is a half-life, which means our base is 1/2 to the power of T is our time over 432. Notice here, since 432 is in years, our T will be in years. So just looking at this, our 1/2 has to be in brackets because we can't multiply the 200 and the 1/2 together because 1/2 has an exponent. Okay? It's just like saying 2 times 3 to the quarter. Okay? You don't get 6 to the quarter. That doesn't make sense. So you just write it as 2 times 3 to the quarter. Now we can see here that this is also going to give us a decay because we have an exponential base of 1/2. So we would expect to see a nice exponential decay curve, which is what we have, except it's being stretched. It has not been shifted, it has been stretched. It has been vertically stretched by 200, which is why our y-intercept that normally would occur at 0 and 1 now occurs at 0 and 200, because 1 times 200 gives me 200. The 432 represent our horizontal stretch. Now we would expect this to increase it because we would take all of our time values, or our x values, and multiply them by 432 in order to shift it. So here they say identify how each of the parameters of the function relates to the transformed graph. Your 200 equals your vertical shift. That parameter is A. And your 432 is your horizontal shift. Horizontal, sorry, not shift, stretch. So we could say that B would equal 1 over 432. Okay? H is 0 here, and K is 0, because it has not moved over, or up and down. Okay, I think we've got one more example here. Oh, no, we don't. So that's it. If you have any questions, feel free to come and ask me. I will be not in the classroom tomorrow, but tomorrow you have your presentation. I will be in the classroom on Thursday morning at 8:15, and we will do our last lesson on Thursday. So there's your assignment. I'll just ask that if you have any questions, again, you either email me or save them for Thursday.